So here the statement of the problem is sort of cluing us in that there may be some weird things going on. It's saying solving a system that is inconsistent or consistent dependent. But of course, we're not always going to know that a system is one of these weird things when we start out. So what we need to do is develop a strategy that will give us those hints along the way. So here's the idea. We're given one of these systems of linear equations and we're asked to solve it. Let's just solve it. Let's just apply the techniques that we already know, either substitution or elimination, to begin the process of finding a solution for each of these systems. And exceptional things are only going to happen if in the process of substituting or if in the process of eliminating to get rid of one of the variables, we also succeed in getting rid of the other. So in a situation where both our x's and our y's happen to disappear simultaneously, then we're going to end up with a third equation which has no variables in it at all. And an equation which has no variables in it at all is either going to be always true or always false. If we get an equation which is always false, then we have a system that has no solution whatsoever. Such a system we call an inconsistent system. There is no solution. There's no point that both of those lines have in common. On the other hand, that third equation with no variables in it could be always true. In such a case, we call the system dependent or consistent dependent, if you like. In such a situation, we end up with a system that has infinitely many solutions to it. And in that situation, we also occasionally want to be more specific about what those infinitely many solutions are. And the way that we prefer to do it is by writing an equation for the line that all these solutions lie on. Looking graphically at these two situations, we will have an inconsistent linear system of equations if we have two lines which do not have any points of intersection. The only way to make that happen in Euclidean geometry is to have two lines that are parallel to one another, so which go in exactly the same direction, but which are separated by some distance. Right? So here the red line and the blue line are parallel to one another, but they're not lying right on top of one another. So they're two different parallel lines, and therefore in Euclidean geometry they have no point of intersection. So an inconsistent system, if we were to graph it, would look like that. Meanwhile, a dependent system is one where there are infinitely many different points of intersection, and the only way to have two lines have infinitely many points of intersection in Euclidean geometry is to make them lie on top of one another. So if both of our equations happen to describe exactly the same line, then that system of two equations is really just a system of one equation which describes an infinite number of points lying along a single line. In that situation, our answer will also ask us to include an equation for that line that both of them lie on top of. And if we do that in slope-intercept format, for example, we can do that just by solving either of the equations because they describe the same thing for y. So let's look at the two examples that were given here and try and figure out whether each of them is either consistent and has a unique solution, consistent dependent and has infinitely many solutions because the lines are on top of one another, or inconsistent and has no solution at all. In the first example, x plus 5y equals 5 and minus x minus 5y equals 5. Let's choose to use elimination because neither of our variables has already been solved for, and choose to try to eliminate the variable that has the smaller least common multiple of its coefficients. The coefficients of the x's are 1s and the y's are 5s, so let's choose to eliminate the x's because it has a smaller LCM. Since the coefficients on our x's are equal and opposite, so I have 1x in the first equation and negative 1x in the second equation, that means that to eliminate x, I should add these equations together. If I add the equations together, the x's are going to go away for sure. So if I add x plus minus x, away they go. Then when I combine the y's, I get 5y minus 5y, and lo and behold, those go away too. So we are indeed in a situation where when we combine these two equations together, all of our variables will have been disappeared. That's what happens on the left-hand side. On the right-hand side, 5 plus 5 is going to give me 10. So when I use elimination to get rid of the x, the y also goes away along with it, and leaves us with this third equation, 0 equals 10. Well, what do we know about that equation? Because all of our variables are gone, and we have an equation, 0 equals 10, which is false. 0 is definitely not equal to 10. That implies that that equation is always false no matter what value of x and y we put into it, and therefore our original system must also always be false no matter which x and y we put into it. There is no x and y that can satisfy both of those equations simultaneously. We have an inconsistent system, and therefore we will say that it has no solution. So if we were to graph these two lines, we would get a graph that looks like this situation right there. We would have a couple of parallel lines that have no point in common of intersection. So that's what happens when all of our variables disappear and we're left with something untrue. Let's look at the second example. X plus 3y equals 3, and minus x minus 3y equals minus 3. Again, because the x's have smaller coefficients, smaller least common multiple for their coefficients, let's choose to target x for elimination. We can do that because the coefficients are already equal and opposite. We don't have to modify the equations at all, just by adding the first equation and the second. Doing so is going to add x and minus x to give us no more x's, so 0. But again, when I add the y terms, 3y minus 3y, the y's also disappear. So we're going to again be in a situation where all of our variables are gone. But in this situation, on the right-hand side, 3 plus minus 3 gives us another 0. And so our third equation is now 0 is equal to 0. And because all of our variables have disappeared and we're left with an equation which is always true, that means that we have a system where if one of our equations is satisfied with a certain x and y, then the other equation will also automatically be true for that x and y. This is an example of a dependent system of equations. If we were to graph both of these lines, these two lines would lie on top of one another. In other words, there are infinitely many points along each of these lines that satisfy both equations. And so the last thing we're going to do here is describe the solution set by coming up with a slope-intercept equation for that line which both of these equations are describing. We can do that just by solving either equation for y. Let's take the first equation. For example, x plus 3y equals 3. To solve it for y, I just need to subtract x from both sides. 3y equals 3 minus x. And then divide both sides by 3. Y is equal to 3 minus x, all divided by 3. Or distributing that division, we get 3 over 3, which is 1, minus x over 3. Or another way to write that is y equals 1 minus 1/3 x. So if in the process of solving a system of linear equations you see all of your variables disappear, your x's and your y's, then either that system is going to be inconsistent, it's going to have no solution at all if the equation that you end up with is false, or if the equation you end up with is true, you get a system which is consistent dependent and so has infinitely many different solutions. Graphically, the first situation of an inconsistent system represents two lines which are parallel but are separated by a certain distance, and therefore never have a point of intersection. And in the second case, you have two lines that are not only parallel, they lie exactly on top of one another. So both equations describe exactly the same line which has infinitely many different points on it that are going to be common to both equations. In that latter situation, we might also want to find an equation for that line in slope-intercept form, which we can do by solving either of the original equations for y. These are situations that do not happen very often in the solutions of linear equations. Almost always, a linear system of equations will have a unique solution. But when this happens, now you know how to deal with it.